The goal of this experiment is to increase the actual laser peak power from 200 terawatts to 500 terawatts, which will mean that we can make here in Vega 2 half of petawatt laser system by improving the laser pulse duration and the focalization of this kind of very broad laser pulses. So the method that we develop is to increase the laser bandwidth in order to have ultra short laser pulses. So from 25 femtosecond to have even shorter laser pulse durations. What I mean is that from 25 we can go below 10 femtosecond or 5 femtosecond. So 25/5, it's a factor of 5 decreasing in the pulse duration, which may be equivalent with a factor of 5 in amplification of the peak power of this kind of laser pulses. And within this method that I propose, which is namely thin film compression, we can demonstrate what the theoretician proposed, that using ultra short laser pulses and lower energy, like a few joules, and sub 10 femtosecond, you can retrieve electrons with GeV energies, which it's fantastic to do that. But we need to prove it. We are the people who should demonstrate that this is possible. The method itself was published or proposed by Professor Gérard Mourou, Nobel Prize in 2018. Since then, I work in his laboratory, and I received this task of implementing this technique at high energy laser facilities, which I already demonstrated. And what is really important is that theoreticians and other experimentalists in laser-matter interaction, they propose novel acceleration schemes, novel methods to characterize laser pulses, and novel application in different fields, but they need these short laser pulses and higher intensity laser pulses, but they don't have yet this. They may go to facilities with petawatt class laser or 10 petawatt class lasers, but what if we can do the same experiments in lower peak power facilities, because the numbers is tens or hundreds of terawatt laser system across the world, and what if we can improve these laser facilities to increase the peak power and do the experiment in many other facilities. We try to solve the problem of the need for more. There are multiple other applications that require higher peak power, higher fluencies, and so on, like particle acceleration, like understanding the universe, understanding how a star is formed or quantum electrodynamics, and all this nonlinear and quantum stuff. They require more power. So at the moment, we are still limited in generating this power. So we are trying to develop new techniques that can be used to increase this actual peak power and to be able to put in evidence, demonstrate these activities that are related to astrophysics, universe formation, quantum nonlinearities, medicine, and so on. We already test this method in multiple other facilities worldwide. We did it also in ELI-NP at 100 terawatt, and then we come here to prove also what we demonstrate in ELI-NP, and to prove again here for 200 terawatts laser system that you have here, and to test a different repetition rate that you have here in CLPU. But each facility is different, has another pulse duration, has another wavelength, and so on, and we try to demonstrate to even more facilities that the method it can be implemented, and secondly, to apply to different experimental use of this technique. So it was demonstrated, but as I said, it's really important to prove in different conditions, and we succeed to do that in other facilities, and we succeed to do that even here at CLPU. So most of the applications of this technique are related to laser-matter interaction, namely electron acceleration, proton acceleration, neutrons production, gamma production, which can be very useful for the further medical developments of in nuclear physics. and also for the demonstration of this laser, improving these laser acceleration capabilities.